So thank you very much for the introduction and also for the possibility that I can give this lecture here. It is also my first online conference lecture. Well, I will try my best. And as Robert has already mentioned, this is joint work with Boris Adamczewski from Lyon and Clemens Müller from Vienna. It's a topic on automatic sequences in a number theoretic framework, and I will start with the most prominent automatic sequence with the 2 and more sequence and also the Rudin-Shapiro sequence as an example. Then I will recall the results on the 2 and more sequence more or less along this subsequence of squares and primes. Then I will introduce the notion of automatic sequences and we'll discuss quickly a very general theorem how logarithmic densities along sequences and automatic sequences can be obtained. And finally, I will present the main results of our joint work, namely that for all automatic sequences, we have the property that along the subsequence of primes and squares, there exists always the logarithmic density of any letter. So let me start with the 2 and more sequence. So there are many different definitions of the 2 and more sequence. I give you just a few of them. So you can start, for example, with 0. Now you proceed always in the following way, that you copy what you have seen so far, but invert. So if you copy 0 and invert, you get just 1. So, and next step, you copy 0, 1 and invert, so you append 1, 0. And the next thing that you have to append is, of course, 1, 0, 0, 1, and so on and so forth. So this gives the 2 and more sequence, and this is actually the recursive definition what I've done so far, but there are other definitions. For example, it can be easily seen by checking this recurrence that the 2 and more sequence is just the number of ones that appear in the binary expansion, mod 2. So if this is also called the binary sum of digits function. So you count the number of ones in the binary expansion or the number of powers of 2 that you need to represent n. And then you count this and take it mod 2. Well, from this definition, it follows immediately that the blocks 0, 1 or 1, 0 just appear consecutively. And this implies that the zeros and ones appear with the same frequency 1/2. So the density of the letter 0 and the letter 1 in the 2 and more sequence is trivially 1/2. The 2 and more sequence has many other properties. I will not go through this, but I will only mention that the 2 and more sequence is a very special case of an automatic sequence. And the automaton that represents the 2 and more sequence is the following one. Actually, this is the minimal automaton that is possible for representing the 2 and more sequence. So how does this work? We have 2 states, and we have 2 possible transitions. So a transition 0 and a transition 1. So if you read a 0, then you stay in this state. If you read a 1, you move to the other state in this example, and here the same thing works. And now what you're doing is that you're feeding this automaton with the binary expansion of n. And every time if you see a 0, then you stay, and every time you see a 1, then you move to the other state till you are done. And then you are in one of these 2 states, and depending where you are, you give an output 0 and 1. And so this gives us the output sequence. So if you take the input of an n as a binary expansion, you see if you have an even number of ones in the expansion, then you will come back to the first state and the output will be 0. And if you had an odd number of ones in the expansion, you will end up in the other state and the output will be 1. So this automaton generates the 2 and more sequence. And more generally, as we see, if you can generate a sequence by an automaton of this kind, and you are feeding it with not only the binary, but the Q-array digital expansion, then all possible output functions of this kind are then called automatic sequences. The next sequence that I want to consider just quickly is the Rudin-Shapiro sequence. This is also a 0-1 sequence, and it is defined also in different ways. Here is a recursive definition or divide and conquer type recursive definition, but you can also trace it back to the binary expansion, and what you are counting here are consecutive 1-1 blocks. So you are counting how many 1-1 blocks you have in your expansion, and then you take it mod 2, and this gives us this Rudin-Shapiro sequence. Or you can also generate it by an automaton. Here we have to use 4 states instead of 2. Well, this 2 and more sequence has been studied in many respects and also in number theoretic aspects. So, for example, we can consider the subsequence of the 2 and more sequence along prime. So, T2, T3, T5, T7, T11, 13, and so on and so forth. And it was a breakthrough result by Modery and Rivard to prove that if you consider just this subsequence of the 2 and more sequence, that the letters 0 and 1 appear again with frequency, asymptotic frequency 1/2, or if you make it as a counting problem, the number of prime numbers up to the nth prime number such that the 2 and more sequence is 0 is just approximately n/2. This was a solution of a long-standing conjecture by Hennenfent. And it should be mentioned that the same result is also true for the Rudin-Shapiro sequence, as Modery and Rivard showed a few years later. Similarly, you can consider not only the sequence of prime numbers, but the sequence, for example, of squares. So you take the zeros, first, fourth, ninth, 16th, 25th, and so on, element of the 2 and more sequence. And again, as a solution of another conjecture by Hennenfent, Modery and Rivard proved this more or less at the same time that the letters 0 and 1 appear again with the frequency 1/2 if you just consider this quite dense, sparse subsequence of the 2 and more sequence. Of course, you can ask whether this is also true for other polynomial sequences, for example, for cubes. This was also conjectured by Hennenfent, but nothing is known about the cubes. So this is a widely open question. There are many results on other sequences, for example, the Piasecki-Shapiro sequence, n to the c integer part, if c is between 1 and 2, but I will not go into this question in this talk. I just want to mention that, again, Modery and Rivard proved a few years ago that the same holds also for the Rudin-Shapiro sequence. And the purpose of this talk is to show that these properties can be actually extended to all automatic sequences. So what is an automatic or Q automatic sequence in general? Well, it's the sequence or the output sequence of an automaton when the input is the Fourier expansion of n. We have seen this already for this example of the 2 or more sequence. So I have here another example for base 3 and 3 states. So the number of states is not necessarily connected to the base Q, but it could be arbitrary, but by chance this is just 3. So here we have some initial state where we start. And now we just read the digits here of, for example, 32. The first digit is 1. So we move according to this transition 1 to the state 2. Then the next digit is 0. So we move to the next state, but the next state is again the state 2 because the transition 0 doesn't change the state in this case. The next digit is 1 and the fourth one is 2. So we move further according to these transitions, 1 and finally 2. So we end up in state 2 and the output is then A if the input is 32. And if we take, for example, 61, we do the same. We read 2, 0, 2, and 1 and end up in state 3 and the output will be then B. And for every input, 32 or 61, we get an output and the output is this automatic sequence. Well, I just want to mention already here that this is a very simple structure of an automaton because the graph that is related to this automaton is here strictly connected. So you can move from every state to any other state. This is not necessarily true in general. You can think of automata that are not strongly connected. So they have some component where the initial state is, but there might be some components where you cannot come back. So we will come back to this question, and this will be a very important observation. Before I move away from this automaton, I just want to give you some other observations here. So these transitions of 0, 1, and 2 can be seen also, or can be encoded by transition matrices. These are just the matrices that relate to the transition 2, for example. So here from state 1, you move to state 3 if you read, sorry, it's the other way around. From state 1, you move to state 2 if you read a letter 2, and so on and so forth. So these matrices encode this automaton. And if you start from the initial state that can be encoded by the unit vector, the first unit vector, then by just multiplying these matrices according to the digits 1, 0, 1, and 2, tell you where you end up. So if you multiply these matrices with the corresponding unit vectors, the place where the 1 appears tells you where you are in the corresponding automaton. So these products encode the automatic sequence. So in general, if you have an input n and with digits epsilon L minus 1 up to digits epsilon 0, this product encodes where you are in the automaton. You just multiply it with the first unit vector and read off some functions. So here this is A, B, and A, for example. This gives us a possible interpretation or a representation of an automatic sequence. This is just one particular approach to automatic sequences. There are others. For example, you can use fixed points of morphisms on finite alphabets, but I will not go into this language here. So actually the number automatic sequence comes from this interpretation of a finite automaton, which is a notion from computer science. Well, These automatic sequences have many properties. And one important property that is also related to the topic of this talk is that every letter of any automatic sequences has a logarithmic density. So you just look at those n where the sequence A of n attains a value alpha and take the logarithmic average of this occurrence and you get the logarithmic density. But this is a weaker form of the density that we have seen before in the two-Morse sequence or in the Rudin-Shapiro sequence. And it is clear that if the density exists, then it has to be equal with the logarithmic density. But there are many cases where the density doesn't exist, only the logarithmic density. But it can be effectively decided whether this density exists, as for the two-Morse sequence or the Rudin-Shapiro sequence. Well, just to mention here that these matrices play some role in this context. For example, if you sum up these representations of matrices, so these products of matrices, up to q to the lambda, so this means that you see all these digits in all possible combinations. This is just the sum of these metrics to the lambda. So this sum matrix that is here in this case is a very simple form, and the powers of this matrix give you actually the powers of them give you an average or information of the average of the states that you end up when you go through this automaton with several inputs. And if this graph that corresponds to the sum of these matrices, so you take just all possible transitions into account, is strongly connected, then you can apply Perron-Frobenius theory, so these powers stabilize, and it follows in this case that you actually get densities. And this is the next observation that I want to make, and namely, if you have a so-called primitive and prolongable automatic sequence, this means that the directed graph corresponding to this minimal automaton, so there's almost a minimal automaton representing the sequence, if this is strongly connected, and if the initial state has a zero loop, this is primitive and prolongable, then the densities exist. And this follows more or less from this property. You just apply the powers of these matrices and analyze them in this case where this matrix is irreducible. And here we have the case there is a zero loop in the initial state, which means that if you just append leading zero digits to the expansion, this will not change the outcome. And also gives you this property that the corresponding matrix is also irreducible in the sense of Perron and Frobenius theory. Okay, so if an automaton is primitive and prolongable, then the densities exist. And this gives us an indication why the following results might hold. And the following two slides give the main theorems that I want to present here. So the first concerns the prime numbers. So we are considering an automatic sequence along the prime numbers. So any automatic sequence. And the result, together with Boris and Clemens, says that for any automatic sequence, the logarithmic densities exist along prime numbers. And we can decide whether these logarithmic densities are not only logarithmic densities, but actually densities. You have to look at the final strongly connected components. So, well, this minimal automaton. So final means that there is no way out of this component. So if you are in this component, you cannot come to another component. So, and if the automatic sequences that correspond to these strongly connected final components, this is automata themselves, and they relate to special automatic sequences, so they are then irreducible and primitive. Then if all these automatic sequences have the property that the densities, well, they will exist, but if for all these final components that might be there in this automaton, these densities are the same, then the whole automatic sequence has a density for all elements of the alphabet, and they, of course, they are the same as the corresponding densities on the final components. Well, and it also turns out that these densities are then rational numbers. So we have a complete answer for the subsequence of primes. So first we have a result for all automatic sequences that there exists a logarithmic density. So this is a far-reaching generalization of the result for the two-Morse sequence and the Rudin-Shapiro sequence. So it gives you a general result, and it can be effectively decided whether the densities exist, and if they exist, they are computable and rational numbers. There is a side result in our paper, namely that there always exists an integer m that is also computable, but there is no nice formula for that. It comes out from the proof with the property that this logarithmic density along the prime numbers coincide if we just consider the logarithmic densities of the sequence along those integers that are co-prime to this number m. So this is a very strange property, and we did not expect that when we started on this work. So the result is complete for the primes, and there is a similar theorem for the subsequence of squares. Again, for every automatic sequence, the logarithmic densities exist, and we have the same property as before. If the automatic sequences that correspond to the final strongly connected components have densities that coincide, so that we have always the same density, then we have a density for the whole automatic sequence along the squares. Well, we expect that these densities, if they exist, are always rational. We could only prove this for prime basis, but we expect that it should be true in all cases. So this is a small open problem in this context. Of course, the logarithmic densities are not always rational numbers. For example, if you take just the leading digit as the automatic sequence, then we only have the logarithmic densities, and it's clear that these logarithmic densities, which correspond to Benford's law, are not rational numbers. There is an alternative way of writing this result. So, of course, if we have an automatic sequence, say this automatic sequence can be, without loss of generality, be complex valued or real valued, and we can also consider these averages with the von Mangold lambda function, or just the average along the squares. The average along the von Mangold lambda function is equivalent of taking averages for prime numbers. And an equivalent formulation of our theorem says that for all automatic real or complex valued automatic sequences, these logarithmic averages or along, well, with weights lambda of n, or just along the squares, always exist. And we can decide whether we can replace these logarithmic densities or means by the usual means. Just to make another example, consider the paper folding sequence that is constructed in the following way, that we just start with 1, and we fold this 1 by taking a fold 1 and appending the converse of the starting sequence 1 the other way around. So here we just append 0. Then we just take a folding 1, and then we append 1, 0, 0, which is the inverse of the starting sequence the other way around. And again, we append a 1, and then we append the inverse of the sequence that we see here. So we append 1, 1, 0, 0, 1, 0, 0, and so on and so forth. This paper folding sequence is an automatic sequence. It turns out that in the prime case, this strange integer m is 2, so it's sufficient to consider odd numbers. And it turns out that the density along the prime numbers of 0 and 1 exist, and they are both 1/2. In contrast, if we just consider squares, then we see that the density along 0 is 0, and the density along 1 is 1. So we see almost only ones in this subsequence of squares of the paper folding sequence. So, of course, we can or could consider also other subsequences. And there is a general result behind that gives us results on subsequences that behave regularly in some sense, and this is made more precise in the following sense. So we just take a sequence that behaves like a power times a slowly varying function. So, for example, log L or whatever, or log L, slowly varying means in the sense that if we just take a linear multiple of L and compare the result with L, then the behavior of this slowly varying function is almost the same, so that they are asymptotically equal. And if we have a sequence of this kind, we call them regularly varying. So, for example, squares, or also the prime numbers, because the prime numbers are more or less L over log L. L times log L. And so they are slowly varying, and also Piasecki-Shapiro sequences, and many other sequences that you might think of are slowly varying. And the result that we have, the first result that we have is that if we have such a regularly varying subsequence, and we take an automatic sequence, then we just have to check all primitive and prolongable automatic sequences first. And if we have the property that for all primitive and prolongable automatic sequences, we have the property that the densities, not the logarithmic densities, but the densities along subsequence exist. Then it follows that for all automatic sequences, the logarithmic densities exist, and if the behavior of the final strongly connected components are all the same, so they have densities and they are the same, then we have also the density along this along the subsequence. So this means that we can trace everything back to primitive and prolongable automatic sequences. So this theorem is elementary but highly involved. So I will not go into detail. But for example, it shows that we get the result for automatic sequence along the trivial subsequence n. So we just take the original, we take all the numbers, because we have already observed that for primitive and prolongable automatic sequences, we get densities because of Perron-Frobenius theory applied to these matrices. And with the help of this theorem, this general theorem, it immediately follows that the logarithmic densities of every automatic sequence along the trivial subsequence n exist. Now coming back to our squares and primes, we just have to show that if we have a prolongable and primitive automatic sequence, then the densities along the subsequence of primes and squares exist. This has been already observed in a previous paper by Müllner for primes. So together with this theorem here, we get the first result for primes. So, but what we had to do actually in our joint work was to prove the same result for the subsequence of squares. Well, for both theorems or both propositions, here there is a similar strategy that, and this strategy goes back to Mauduit and Rivard. But in order to handle this strategy for all automatic sequences, we need another input that has already also due by Clemens Müllner, namely that a primitive and prolongable Q automatic sequence can be represented in the following form. So there exists a synchronizing automatic sequence and another sequence T of n. So that is very close to an automatic sequence. I will explain it in a minute. So that if we have this sequence S of n and T of n, then we can get back A of n. And S of n has a very simple structure. It's synchronizing, which means that it's almost periodic. So asymptotically, we can get distributional results of synchronizing sequences just by considering residue classes. I don't want to explain this in more detail, but the only information that we need is that we can restrict to residue classes. And T of n is a sequence that is group valued. So, and it behaves very similarly to the sequence that we had in our example before. So if nq plus j just means that we already know what is going on for n, and then we just append a digit j in the expansion. So we have expansion of n, cubic expansion of n, and then we append a digit j, and then the result of this should be T of n times a group element. And this group element depends more or less on j, but also on S of n. But S of n is more or less periodic. So let's avoid this dependence or put this away for a moment, this dependence of S of n, and just consider that. Then this is precisely the same property that we had before for this representation with these matrices. And in this example for before, these matrices were actually invertible matrices. They have been permutation matrices. And here, in this case, we have again this kind of property that this here we have a group, and these matrices, this permutation matrix, well, of course, are invertible matrices. They form a group of unitary matrices, and here this is very close to this automatic sequence. If we avoid this S of n here, then we get a kind of automatic sequence that is group valued, which means that it has it can be inverted. And this gives us another technical input. So if we have a group valued function, then we can apply representation theory to get distributional results, and this will be actually applied. So we can reduce an arbitrary prolongable and primitive sequence to a more or less periodic part and a group valued more or less automatic sequence. So this is a very important information. Sorry. Now we are adopting, or have to adopt some notions that go back to Mauduit and Revard, that are called carry property and fourier property. So I will not explain this in detail. I just want to mention that the so-called carry property says that if we add a small number to a big number, then only very few digits are actually changed. And this should have almost no effect to the function f of n. So if this function f of n is in some way consistent with the digital expansion and also reflects these addition properties in a proper way, then this is the carry property. And our automatic sequences have this carry property just by definition, because they depend heavily on the digital expansion, and if we just change some digits, the other digits will not be changed. And the second property, which is very important, it's very important, is the so-called Fourier property, which says that we have that the Fourier transform decays properly. So what we see here is more or less a discrete Fourier transform of these values. Suppose that alpha is 0, then we just have the discrete Fourier transform of this f, and this f is group valued, so it has unitary matrices as values. So this are not numbers, but they are matrices. So we take the Fourier transform of these matrices, and they should decay in lambda. So if we just take bigger intervals, q to the lambda, if lambda is going to infinity, this should go to 0 sufficiently fast. So this can be translated in several ways. There is also a version to translate it into Gauss norms, but just think of a Fourier property in the sense that the Fourier coefficients decay sufficiently fast. And if this such a function has these two properties, then it follows that if we take von Mangold lambda function and also an exponential part that can take care of periodicities later, then this function or these sums are small compared to x, as it stated here. So this is just a statement that these sums, so this function f times lambda mixes. So that we have a saving for these exponential sums, or in other terms, so we can say something on the distribution of f of n on primes. So this result goes back to Mauduit and Revard and has been generalized by Müller to the case where f is not real valued or complex valued, but has unitary matrices as values. And a similar result that we could generalize here for this purpose of squares is again a generalization of Mauduit and Revard from a few years ago, where if we have the same property of the function f, that it satisfies this carry and the Fourier property, then if we just the subsequence of squares, then we have some saving if we sum up. Okay. Now we are almost done. what we have to do is that we have to apply this for d of t of n, where d is a unitary and irreducible representation of the group G, where this sequence t of n lives. So t of n is related to this representation of an automatic sequence. So while we had this factor, so these exponential factors here, so they can take care of S of n, which is almost periodic. So, and now we just do some Fourier analysis on the group G. This gives rise to this representation, and consider, as I mentioned, residue classes for taking care of S of n, and this can be used to get this, the distributional behavior of the sequence A of n along primes and squares. Okay, and this gives us the theorem, so these two propositions for A of n along primes and along squares, if we just consider a primitive and prolongable automata or automatic sequences, and together with the general theorems, we get then the whole result. So thank you very much for your attention. Questions?
Yeah, thank you very much, Michael, for this nice talk. I have a question immediately. You mentioned this number m, which can be chosen, and it's computable such that the coprime numbers give the subsequence along primes. So how big is this number m?
Well, this depends. Well, of course, it could be, well, it really depends on the, you have to look to the proof. So you have this so you have this automaton, and that is, you have that, yeah, well, how shall I say this? So this depends on the specific representations that that have to be considered separately, and this so there is no simple formula on that. So I cannot.
No, but an asymptotic estimate or something like that. If
no,
it is, no. Is it growing? What are the ingredients from which this number is dependent?
Well, it depends on the. You have an automatic sequence, and this automatic sequence corresponds to a finite automaton. And this finite automaton has strongly connected components. And then you look at these strongly connected components and the automatic sequence related to the strongly connected components. And this special automatic sequence have these representations together with some synchronizing sequence, and say in a sequence that is group value T of n, capital T of n. And now you have this group G's according to these strongly connected components, and then you have to analyze these representations that on this group, and there are some exceptional representations that have to be considered there, and from these exceptional representations you get out this number. So it is not a formula, and it's I'm not sure that there is an asymptotic formula on that. That is just,
at least an upper bound.
We did not think about that, but it's it's an interesting question. But for these simple sequences, this is just m equals 1 or 2.
There is a chat by Clemens Müller. I think it is at most exponential. So thank you very much. If that is true, this is an answer of good.
Okay, I'm sorry. So I did not. So it was more his part to do this, but yes, the answer is exponential. Thank you very much, Clemens.
At most exponentials, he says. Okay, so okay, maybe that can be. Yeah. Okay. So thank you very much. Are there other questions? So maybe this is also a question for the problem session. If it is really exponential, or if there are automata where it's polynomial or whatever.
Well, it's very strange that this property is not true for the squares. So there is no corresponding property. At least we could not find that. So it might be another question if there is a similar property for prime. But our guess is that for squares. So our guess is that primes are more or less random in some sense, and therefore they behave nicely. And from this random property, we get that more or less. But for squares, they are too regular to have this property. It's not a precise statement, but this was our observations. We first thought that there might be something also for squares, but it turned out that we could not find that.